Hi class, today we're going to learn about factoring polynomials. So we're taking what we know about polynomial division and synthetic division and using it to factor. So in this note, we'll also learn something called the factor theorem and the remainder theorem that will help us learn how to factor polynomials, and we'll also use it a bit in problem solving. So first, let's start with the definition of what a factor actually is. So let's say, for instance, that I wanted you to tell me all the factors of 12. Well, the factors of 12 are all the numbers that multiply evenly into 12. So 1, 2, 3, 6, and 12 are all factors of 12. Now, another way of thinking about this is that when you divide by any of those, you get a remainder of 0. So the same is true when you're dividing polynomials. So a polynomial is a factor of another polynomial if, when divided, the remainder is 0. So in order to factor, really we're just trying to find polynomials that have a remainder of 0 when divided by the other polynomial. So if I tell you that 2x plus 3 is in fact a factor of this polynomial, then that means when I do synthetic division, I will get a remainder of 0. So let's set this up and I'll show you what I mean. So I get 6, 5, minus 16, and minus 15. Now out here, I need to put minus 3 over 2, since that would be what would make 2x plus 3 equal to 0. Okay, I bring down my 6 and I go through and do the synthetic division. Okay, I'll go through this rather quickly since this is not the focus of today's note. That's the focus of yesterday's note. So I'm just kind of filling it in. So notice here I get 15 and my remainder is 0, which it should be since 2x plus 3 is a factor. So that means that this polynomial can be rewritten in a different way. It can be rewritten as x plus 3 over 2 times 6x squared minus 4x minus 10. Now remember, when you have a fraction here, you have to do a little bit of work to get it to look like this 2x plus 3. So I need to kind of borrow a 2 from this factor and put it into this factor so that I get 2x plus 3 here instead of x plus 3 over 2. And then that means I get 3x squared minus 2x minus 5. Now this is just a quadratic, so we can factor it using the same methods that we learned in grade 10 and grade 11. Okay, it's a complex trinomial, so you use decomposition. The 2x plus 3 stays out front, and when you factor this, you get 3x minus 5 and x plus 1. So that means 2x plus 3, 3x minus 5, and x plus 1 are all factors of this original polynomial. So this is the factored form of this polynomial. Now this also means if I had used negative 1 in the synthetic division, I would also have gotten a remainder of 0. If I had used 5 over 3 in the synthetic division, I would have also got a result of 0. Try it, see if you get it. Okay, so how do we actually get to factoring though if we're not given one of the factors? In that example, we were given one of the factors so we could find the other two, but obviously that won't be the case. Now, this next section is quite confusing for some students, so just bear with me. You might not understand why I'm doing what I'm doing as I go, but I'm working toward explaining a theorem called the remainder theorem. So remember from yesterday, if we have a polynomial, okay, that we're dividing by x minus b, then we can write the result as p at x equals the quotient q at x. So I'm just going to make that a bit clearer. P at x equals q at x, where q at x is the quotient, times x minus b plus r, where r is the remainder. Okay, remember that's just how we wrote answers last time. So whatever the polynomial is whatever the quotient is times the divisor plus the remainder. Now, we also talked about it being written in another way, but this is just the way we're going to focus on today. So how can we use this information to determine if a polynomial is factorable? Okay, so let's say the polynomial we're given is this 2x cubed plus x squared minus 3x minus 6. So over here to the side, we can just say let p at x be equal to, I don't know why I'm having such a hard time with this, 2x cubed plus x squared minus 3x minus 6. Okay, so what happens when we divide by x plus 1? Okay, so what we're going to do is we have our p at x, and when we divide it by x plus 1, we'll have the quotient times x plus 1, because that's what we're dividing by, plus whatever remainder we get. Okay, so watch what happens when I put negative 1 into this function. Now I'm choosing negative 1 because that would make this guy equal to 0. So on the side, you can put x plus 1 equals 0, so x equals negative 1. So I'm putting negative 1 into this function. So p at negative 1 is equal to q at negative 1 minus 1 plus 1 plus r. So notice what happens here, okay? Because I chose negative 1, that makes this bracket equal to 0, which is why I chose it, right? And because this is equal to 0, and it's being multiplied by this, in fact, this entire product will equal 0. So what that means is that p at negative 1 is just equal to r. So what does that mean? That means if I put negative 1 into this function, I will get what the remainder is when I divide by x plus 1. So p at minus 1, if I put it into the function, I get out a negative 4. So that means the remainder of that division question is negative 4. That's kind of interesting. So if I divide 2x cubed plus x squared minus 3x minus 6 by x plus 1, the remainder will be negative 4. I know that because when I put minus 1 into the function, I get negative 4. Now, does that work if we have a divisor where we have an a value out here? So now my p at x is this long thing. Okay, that's my p at x. And then I also think about what would make this equal to 0. So I'm going to put minus 2/3 into the function. So recall that p at x equals my quotient times 3x plus 2, since that's what I'm dividing by, plus whatever the remainder is. So when I put in minus 2/3, I'm going to get q at minus 2/3. Now, when I put it to minus 2/3 into here, I know I get 0. That's the whole reason why I chose it, right? Plus r. So yeah, this goes away, and I just get p at minus 2/3 equals the remainder. So when I want to divide by, when I want to know the remainder, when I divide by 3x plus 2, I put minus 2/3 into the function, and that gives me the remainder. Now, you might think that the remainder isn't very special, but it is special when you're factoring, because when you're factoring, all you care about is that the remainder is 0. So I'm going to show you the remainder theorem first, which leads into the factor theorem. So when a polynomial is divided by ax minus b, the remainder is equal to f at b over a. Now, you might think, Mrs. Wiens, where did b over a come from? Well, when you set ax minus b equal to 0, you just get x is equal to b over a. That's where that came from, okay? So what does this mean? This means that, for example, if I have this f at x divided by this, if I want to know the remainder, all I have to do is find f at 3, which in this case, I believe, is 14. If you put 3 into this function, you get 14. So that means the remainder of that division question is 14. So this becomes useful when we want to factor. So the factor theorem then is that ax minus b is a factor of f and x if and only if f at b over a is equal to 0. So the factor theorem follows directly from the remainder theorem. Okay? So that is an important piece of information. So when you put a number into a function, if it equals 0, then it's a factor. Okay? You can also relate this to your understanding of graphs. Okay? If we have some function that looks like this, okay, its factors are the same things as its zeros. Okay? So it makes sense that when you put in these numbers, you would get a y value of 0 because the factors also tell you the x-intercepts. So that should all kind of combine together in your brain. So I'm going to do something kind of different. I'm going to go right to example 6 because example 6 is a different type of example that doesn't have anything to do with factoring in this note, but it really has to do with understanding the factor theorem. I found in the past that if I leave this example to the end, students have gotten so focused on the actual factoring that they've forgotten what the factor theorem and the remainder theorem are. So let's go to example 6. And it's important that you understand this example because this type of question is asked again, I believe, on a test or even the exam, because it really tests your understanding of the factor theorem and the remainder theorem. Okay, so when this function is divided by x plus 1, the remainder is 12, negative 12, and x minus 2 is a factor. Find m and n. Okay, so we really have two pieces of information. We have when it's divided by x plus 1, our remainder is negative 12, and then we have that x minus 2 is a factor. Now, it's important to interpret that information to mean that the remainder is equal to 0. So anytime you see that something is a factor, you should think, well, that means the remainder is 0. So the remainder theorem states that f at negative 1 should be equal to negative 12 then, because when you put minus 1 into the function, it equals the remainder of that division question. And we know that the remainder is minus 12. So what we need to do is put in negative 1 for the function, and set it equal to negative 12, okay? When we simplify this, well, it'll result in an equation with just m and just n, okay? So what we're going to do over here is this means that f at 2 is going to be equal to 0. So similarly, we can put 2 into the function and set it equal to 0. So 2 times 2 cubed minus m times 2 squared plus n times 2 minus 2 equals 0. So when we solve this equation, also we'll come up with an equation that only has m and n. So we'll have two equations with two unknowns, which we can solve using substitution or elimination. So when you simplify this, you get m is equal to 8 minus n. So try it. Make sure that you actually can rearrange it for that. All I'm doing is just going through the algebraic steps there. For this one, I get that minus 4m plus 2n equals negative 14. Okay? So again, try it. Make sure you get that. So now I just use the method of substitution to substitute 1 into 2. Okay, so instead of an m here, I'm going to write the 8 minus n. So minus 4 bracket 8 minus n. This is just from grade 10. Hopefully you guys remember. Goes minus 14. So now I have an equation with only one variable, so I can solve for n. So I get there, when I expand and collect like terms, I get that n equals 3. And then using equation 1, I get that m equals 5. So that's my final answer. So I found m and n. So that means the polynomial that would work here is, I'm going to use a different color, 2x cubed minus 5x squared plus 3x minus 2. That a polynomial would satisfy these different situation. So when it's divided by x plus 1, it would have a remainder of minus 12, and x minus 2 is a factor of that equation. Okay, so that is an example where you use your understanding of the remainder theorem and the factor theorem to solve a problem. Okay, like I said, it tests that you actually understand what those two theorems are, and that's why it's an important question for me to include in something where I'm testing your understanding, because it tests your understanding of those two theorems. Okay, now let's get to the core of what we're actually here for, and that's to learn how to factor. So when I give you a question like this, you have to know how to factor that. That's the basis of what we're doing here. So the unfortunate thing is that factoring for polynomials greater than degree 2 involves some guesswork. Now it's going to be educated guesswork, but it is guesswork nonetheless. Hate to break it to you. So what helps us though is that, okay, let's look at this example first here. We know, since this is of degree 3, that it's going to have likely 3 factors. Okay, so let's say that those factors are x minus b1, x minus b2, and x minus b3. Now I want you to think about what's special about b1, b2, and b3, because those are the numbers we're trying to find. We're trying to find what the factors are. Well, notice that when you expand this all out in order to get from this to here, that b1 times b2 times b3 has to equal 24 in order for this right side to equal this left side. So that's an important result. b1 times b2 times b3 has to equal 24. So therefore, b1, b2, and b3 must be factors, so are factors of 24. So when I'm trying to figure out what my factors are, I wouldn't try 5, for instance, because 5 is not a factor of 24. So only certain numbers are possible for the zeros, which would be any of the factors of 24. So therefore, you can go back up here, factors of the form ax minus b must have a b value that divides into the constant term, right? The last term, and this is y. So when I'm checking out this example here, I don't want to test every number under the sun. I just first want to identify my possible factors. So the possible factors here are anything that -6 is divisible by evenly. So plus or minus 1 are both factors of -6. Plus or minus 2, plus or minus 3, and plus or minus 6. So I have 1, 2, 3, 4, 5, 6, 7, 8. 8 different possibilities, and probably only 3 of them will work since this is a cubic. So there's 2 different ways of finding what these actually are. Okay, just a hint already, I prefer method 2, but I'll show you method 1 first. So method 1 is using the factor theorem. So basically, this just means you guess and check. So guess and check f at b until you get it to equal 0. So for instance, let me try f at 1. Okay, if I put f at 1 into this function, I get 1 cubed, so 1 plus 2 is 3, minus 5 is minus 2, minus 6. So I do not get 0, so therefore I can say x minus 1 is not a factor. Okay, so now I can either try minus 1 next or plus 2. I'm going to try 2 because, spoiler alert, 2 is a factor. So let's put f at 2 in. So if I put f at 2, I get 8 plus 2 times 4, plus 8, which is 16, minus 10, minus 6. So that equals 0. So woohoo, that means x minus 2 is a factor. Woohoo, yay, cartwheels. Okay, so that means then I want to go through and do my synthetic division with 2 here to see what my answers are. So then I would put in 1, 2, minus 5, minus 6, and do the synthetic division. Okay, so I get a remainder of 0, so that confirms what I thought. But now I know that when I do x minus 2, what I have here is x squared plus 4x plus 3. Okay, and then that's just a quadratic. So you get, I'm behind my head now, aren't I? Okay, x squared plus 4x plus 3, that factors to x plus 3, x plus 1. So now I'm done. I have my fully factored form. Okay, that's method 1. Method 2 basically just makes it so you don't have to use the factor theorem. So method number 2 is just going right to synthetic division. So basically you practice synthetic division until you get a remainder of 0. Okay, so you set up your synthetic division, and I always use pencil so I can just erase. So I have 1, 2, minus 5, and minus 6, and I know that I need a 0 here. Okay, so that means I know I need a 6 here actually, right? So anyway, so I already know that 1 doesn't work, but I'll show you using synthetic division how I would do this. So I put a 1 here. I bring down my 1. 1 times 1 is 1. Okay, I go through and do this synthetic division. Well, that doesn't work because I don't get a remainder of 0. So erase, 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 erase. So now I'm going to try the next number 2, and I'm like, please let me get a synthetic or a remainder of 0. And you already know that I will. Awesome, woohoo, I did get a remainder of 0. So that means that I can go right to x minus 2, x squared plus 4x plus 3. Okay, and again, now I just have to factor that quadratic, which is x plus 3 and x plus 1, so I get the same result as before. The reason I like this better is because you can basically skip this step, because if you do this factor theorem step, you still have to do synthetic division later. At least then you'll know this synthetic division works. But in this step, when you find the synthetic division that works, then that synthetic division step is already done for you. So you can use either method, but I always myself just use method 2, where you go right to synthetic division. Now notice if I had put in -1 in here, it also would have given me a remainder of 0. And then my resulting quadratic would have just factored to these two guys. Okay, so, or if I had put in -3, I would have gotten a quadratic that would have factored to these two guys, okay? So it doesn't matter which one you find first. When you get down to the quadratic, you'll find what the other two are. Okay, so that's something important to keep in mind. So that's an example when your divisor is just of the form x minus b and you don't have an a value. So I would encourage you at this point to go to the first practice question on the back page, the one that has plus 24 as a constant, and try that practice question before we get into the next level of difficulty. Okay, so the next level of difficulty is when you have an a value that is not 1. So ax minus b is a factor. So remember that the b value is just a factor of the constant term, and I already explained on the previous page why that's true. But the a value is a factor of the leading coefficient. Okay, so why is this true? Well, it's kind of the same thought as the other one. So if you have a1x minus b1 times a2x minus b2, all the way to however many you have a(n)x minus bn. When you multiply that all out, a1 times a2 and then times all of the a's together will equal the leading coefficient. So that means that these guys have to be a factor of the leading coefficient. So if you're testing fractions, it would be of the form b over a, where b is a factor of the constant of the polynomial, and a is a factor of the leading coefficient. Okay, so let's try this with example 3. So the first thing you always want to do is identify your possible factors because you don't want to go through and start doing the synthetic division with things that don't matter. Okay, so first I just look at my integers. Okay, so up here it says check the integer factors first. So the integer factors are those that are just factors of the constant. So what are factors of 2? Well, plus or minus 1 and plus or minus 2. Okay, so those are my 4 possibilities of factors that are integers. Now I have to consider fractions that on the top are factors of this guy, the constant, and on the denominator are factors of the leading coefficient. Okay, so the factors of my leading coefficient are 1 and 3. So I would have 1 over 1, which is just 1 when I have, which I already have, so I don't have to include that, or 1 over 3, and then plus or minus. And then 2 over 1, which I don't need to include, or 2 over 3, and they can be plus or minus. So here I have 1, negative 1, 2, negative 2, 1/3, negative 1/3, 2/3, and negative 1/3, 2/3. All that are possibilities for me to put into my synthetic division. Now, not all of them are going to work. Only 3 of them will. So I always want to start with trying my integers before I start those gross fractions, right? And guess what? Chances are that one of the factors will always be an integer. So I've never actually seen it where you have to go to the fractions to find a possibility. Usually those can come out when you're factoring the quadratic. Okay, so I'm going to try 1 here. So I have 3, 2, negative 7, and 2. Bring down my 3, 3, 5, 5, negative 2. Oh, yay! I get a remainder of 0. Exciting times. So that means x minus 1 is a factor, and then I still have 3x squared plus 5x minus 2. Okay, so now this is a quadratic, so I can use decomposition to factor that. So I get 3x minus 1 and x plus 2. So that means if I had put 1/3 here, it would have worked. If I had put negative 2 here, it would have worked. So obviously, though, it's easier for me to find the 1 or the negative 2 than it is for me to deal with this fraction 1/3, and that just came out here when I did the quadratic factoring. So try to leave it to the last choice. Okay. At this point now, you guys can try. You can try example 2 in the practice, which asks you to sketch. Okay. Notice that you can common factor out a 2x before you actually do your polynomial, your synthetic division. Okay. All right. So now I'll do a couple of examples that involve factoring by grouping. So if you'll recall from grade 10, factoring by grouping just means that you're looking at the first 2 terms and the last 2 terms. So in this case, you can common factor out x squared and you're left with x plus 2. And if you common factor out a minus 9 here, you're left with x plus 2. So I know this is working because I have a common factor of x plus 2. So I can take that out, and then I'm left with x squared minus 9. Now, x squared minus 9, you always have to ask yourself, can I factor further? You can't just stop at that step. And yes, you can, because x squared minus 9 is a difference of squares. Okay, so there we go. So if I wanted to sketch this, for instance, now I know that I have a 0 at negative 2, at negative 3, and at positive 3. I know it's a cubic with a positive leading coefficient. These zeros are all of order 1, so it would look something like this, and I could find my y-intercept, okay, which is negative 18. And I would label all these. So that's why factoring is useful, because now, before I had no idea how to sketch this, and now with the zeros, I do. Okay. This also you can factor by grouping. Okay. You'll know right away if you can factor by grouping is that when you take out your first terms, if you get the same thing in these second brackets. So in both of these cases, I did. I common factored out an x cubed. I was left with x minus 6. Then I common factored out 2, and I was left with x squared minus 6. Oh, sorry, this should be well, 2x that I take out. So that 2 shouldn't be there. So I'm left with x minus 6. There we go. So I have an x minus 6 out front and an x cubed plus 2x in here. Now, am I done? Is this fully factored? No, because I have a common factor of x that I can take out here. Okay, now can I factor x squared plus 2? No, I can't. It's not a difference of squares, and there's nothing else I can do there, so that is fully factored. Okay, we already did example 6. So now you have some practice questions, okay? So I realize that this has a million factors. It's 24, but I still want you to start with your list of possible factors. And there's a lot of them, so come up with those, okay? Now I'll give you a hint. Your final answer should be, well, more than a hint. I'll give you your final answer to make sure you did it right. There you go. Okay. And for this one, like I said earlier, you can common factor out a 2x first, which makes it a lot easier. Okay, so now you gotta keep the 2x out here, but now you just gotta worry about factoring this guy. Okay, so when you do that, your solution should be 1, 2x plus 1, x plus 2. Okay, and so then you should be able to sketch that, knowing what your zeros are and what the order of each zero is. Okay, now alternatively, if you hadn't taken out the 2x first, you can still factor it. It's just that you would have 2 levels of synthetic division. Because this is a quartic, you would have 2 steps of doing it the synthetic guessing way until you get down to a quadratic. Okay, so you just have to keep doing the synthetic division guessing method as many times as you need to until you get down to a quadratic, and then we have those other methods of factoring. So let's take a look at what your success criteria are. Can you define what a factor is? Can you define the remainder theorem and the factor theorem formally and in your own words? Can you identify what the possible factors are if I give you a polynomial function? Can you use the factor theorem or synthetic division to find what if something is a factor, and then factor a polynomial? Can you factor using grouping if it's possible? And can you do something like example 6, where you're given facts about remainders or factors, and then you try to create true statements? So that is your note on factoring polynomials. I'm going to do another note now on factoring using a difference or a sum of cubes, which will be a shorter video, but I may ask you to watch these videos together in one night. Thanks for watching. Hope you learned lots.